All right, happy Monday. I hope you had a great weekend and stayed out of the smoke. It's starting to get a little tiring, of course, but hopefully we'll see some clearing of that soon. Um, we are now 1 week away from our first exam. So that's coming up a week from today. So you'll get an idea for what exams are like then. The exam, I sent some details about the exam on a recent email on Friday. Hopefully you're all getting those emails. Just give me a big thumbs up if you got it. Okay, it looks like most of you are getting it. If you're not getting my emails, it's going to your Pipeline account. And if you're not getting them, make sure you email me and we'll figure out what's going on, okay? But anyway, the details about the exam are there. The exam is gonna be on Monday. It's gonna open at 2, the time the class usually starts. We will not be having class on Monday, so you can take the exam. And then it'll close at 10, and you'll have 60 minutes to complete the exam, okay? And you'll do that through Canvas, all right? I wanna encourage you to take advantage of the tutoring. Let me just share my screen here real quick so you can see that. Let's see. Can you see my screen? No, that didn't work. Stop share. It's the wrong screen. Share screen. There we go. These are the times that tutoring are available. So notice, beginning Wednesday, you have pretty much all evening Wednesday, most of the day Thursday, and most of the day Friday, where there's someone going to be online waiting for you to come and talk to them and get help. All right. So you might be working on your problems. You might be studying for the exam. Whatever you're doing, you can get help at all these times. And all 3 of these tutors are very, very good. Those of you that have been to them, and I know many of you have, already know that. Those of you that haven't, make sure you're taking advantage of this. All right. You can even just log into their Zoom during those times and work on a problem set or work on studying. And then when you have questions, you can ask them questions. They're there to help you, and they're very good. Other sources of help, of course, are myself, which you can talk to me either immediately after class, anytime we have class, and then also Tuesday and Thursday by appointment. Just send me an email and I'll set you up, and you can have an appointment with me via Zoom and get your questions answered. Okay. Now, let me see if there are any questions. Do you have any questions? Thank you for turning your cameras on. I can see a lot of you now. The ones that have the camera on float to the top, so it's really super helpful for me. So thank you for doing that. Any questions? Use the raise hand function, which is under participants, if you want to ask me a quick question. Yeah, Jada.
Yeah, last lecture, we quickly went over like acids, and I was wondering if you were gonna go over it again.
Yep, I'm gonna go through it right now. I'm gonna do a couple more examples.
Okay, perfect. Oh, I didn't see that. Thank you.
Yeah, it did go really fast.
Yeah, awesome. Thank you.
All right, thanks, Jada. Hey, Yoon.
I just had a quick question about the pre-tests, if it's okay.
Yes.
For the pre-test, do we have to take it like next Monday, or can we take it like earlier?
It just opened today at 2 o'clock, and it'll remain open until you can take it anytime from now until next Monday.
Okay, is it more recommended to like take it first, obviously before the actual test?
Well, you have to take it before the actual test because it's only available until 2 p.m. on Monday, and it's due it's due on 2 p.m. on Monday. And the actual test opens at 2 p.m. on Monday. So the idea is you take the pre-test before the exam, and you use that as a way to make sure you are prepared for the exam.
Oh, okay. Thank you.
Yep. What else? Any other questions? I hope everything is going smoothly. I'm for all of us, this is new. And so I hope it's going smoothly. If it's not, I want to hear from you, right? If there are some issues in terms of the way the class is going, please either send me a message or ask me in class or send me an email. My goal is, of course, for you, my main goal is for you to learn, right? For you to learn the material. You're supposed to learn whether we're online or live, right? My goal is for you to learn chemistry. The test is, the pre-test is not timed. You can take all the time you want for the pre-test. The pre-test has no restrictions in terms of materials you can use. The pre-test is really designed for you to help you continue to learn the material. So what we call formative assessment, right? And so the actual exam is timed, all right? And you have 60 minutes. All right, let's see. Abe, you have a question? Abe De La Palma, are you there? I'm not hearing you, Abe, if you're talking.
Oh yeah, is the pretest gonna cover information from just from last Wednesday, or will it also cover information from this Wednesday?
Both the pretest and the exam are over chapters 1, 2, and 3. All the material that we've covered so far, plus what we've covered into today and Wednesday.
Okay.
Yeah. Anything else? Okay. Very, very good. All right, so let's go ahead and get started. At the end of last time, as you remember, and some of you have already asked, we were sort of going over nomenclature, right? And we got through a few things, and we rushed towards the end to get through acids. So I'm just going to do examples of all the different classes one more time, including acids. And if you still have questions after that, feel free to ask me, okay? So let's just try naming each of these compounds, all right? And that'll kind of show you how to use this chart, which kind of organizes the way nomenclature works. So the first question to ask yourself when you're naming anything, right, is what is it? What kind of thing are you trying to name, all right? So this first one, let's see, calcium iodide, right? So, sorry, I said the name already, CaI2. Let's go ahead and try to name that even though I already gave it away. The first thing you gotta decide is it ionic, is it molecular, or is it an acid? What do you think? CaI2.
Ionic.
It's ionic, right? How do you know it's ionic? You know it's a metal and a non-metal. How do you know it's a metal and non-metal? Calcium's on the left side of the periodic table, iodine's on the right side of the periodic table. In other words, calcium is in the metals section of the periodic table and iodine is in the non-metal section, all right? So you kind of have to know that, and you have to, and it's helpful to have a periodic table in front of you, although we don't have one right here on screen. All right, once you decide it's ionic, then you have to decide what kind of metal is in the ionic compound, right? So ionic compounds are gonna be a metal, non-metal, and there are two types, right? There's metals that form only one type of ion. That is, they always have the same charge in all their compounds, all right? And then there are metals that in some compounds they have one charge, and in other compounds they have a different charge, all right? So that's the decision you have to make. And again, you have to have a periodic table to know which one it is, right? So calcium turns out to be a group 2 metal, and it's of the type that always forms the same charge in all of its compounds, okay? So it only forms one type of ion, right? And then you go down this, and then you see how you name it. You have the name of the cation, okay? That's calcium, right? And then you have the base name of the anion, so that's iod, right? And then the ending ide. So the name is calcium iodide. All right? Let's try another one. FeCl3. First of all, what is it? Ionic, molecular, or acid?
Ionic.
Yep, ionic, very good. Then we got to go down here. We look at the metal. The metal is iron, Fe. Is this a metal that forms only one type of ion, or a metal that forms more than one type of ion?
More than one.
More than one type of ion. It's a transition metal. Most transition metals are of this type, okay? So we know then that we have to include a Roman numeral that gives you the charge of the metal, right? So we know that this is going to be iron, right? And now we got to figure out its charge, right? How do we figure out the charge of the iron? Well, we got to do it by deducing it from the compound itself. We see that it's paired with chloride. Chloride is -1, right? there are 3 of them. So these 2 together are -3. So what's the charge on iron?
3 plus.
Exactly right. 3 plus. So we're going to write in Roman numerals 3 plus. Okay. Iron, or just 3, iron 3. All right. And then the base name of the anion, right? Plus the ending I. So that's going to be chloride. So the name is iron 3 chloride. Does that make sense?
I have a quick question.
Yeah.
So there was a problem on the problem set,
Yes.
and it was asking for, well, it said iron Roman numeral 3 and then chromate.
Yes.
It was asking for it in the like Fe form.
Yeah. For the
and
formula.
so the answer was Fe2 CrO4 parentheses 3. But that, I was confused by that because that doesn't seem balanced, the 2 and then the -6.
Because each iron is 3 plus, right? So if there's 2 of them, that's +6. And then the 3, there's 2, yeah, Fe3, so the 2 of them. And then for the chromate, there's 3 of them, so that's -6.
Because isn't, don't we not know the charge on Fe?
Right, you don't, but you know the charge on chromate.
Yeah, it's -2.
Right. So so tell me what the name was again, and we can do that right now. It was
Okay, so
iron
it was iron 3 chromate.
3 chromate. Right. So so if the chromate is if the chromate is -2. Oh no, sorry. They gave you the name or the formula?
They gave you the name, and then
Name.
they asked.
Okay, you're trying to write the formula. Okay, good. So then you know that it's got to be iron 3. So you know this is 3 plus, and you know that chromate is -2, right? So how can you make the charge be equal on both of them? You got to have 2 of those, and then the chromate is CrO4, correct?
Yeah.
And you got to have 3 of those.
Okay.
Right? Because the 2 of these, right, add up to 6 plus, and then each of these is -2 times 3 is -6. So this ends up being times 2 equals 6 plus, right? This is 2 minus times 3 is equal to 6 minus.
Okay.
Does that make sense?
Yeah, so the 3 tells you the charge on the chromate, or like
No. The 3 tells you the charge on the iron.
Okay.
So you know it's iron 3, right? And then you know, so you have something that's 3 plus, then you have something that's 2 minus. How can you make that charge balance? The only way to do it is to have 2 of these and 3 of those.
Okay. Yeah, I get it now. Thank you.
Great. Okay. All right, let's continue. Good question. Next one is P2O5. So first of all, we got to decide, is it ionic, molecular, or an acid?
Molecular.
Molecular.
Molecular, right? Non-metal and non-metal. All right, so we're going to go down. And here's where we use the prefixes, right? So we know that we have 2 phosphoruses, right? And 5 oxygens. So we're going to name this diphosphorus. And then what? This is an oxygen, right? And how many of them are there? 5. So it would be what?
Pentoxide.
Pentoxide, exactly right. And I would accept either pentaoxide or pentoxide. Usually when you have 2 vowels, you drop one and just write the second one. But if you wrote pentaoxide, that wouldn't be any big deal at all, okay? Okay, let's go on to this one, H3PO4. Ionic, molecular, or acid?
Acid.
Acid.
Acid. And how do you recognize it's an acid? Whenever you see an H up here in front, and then you have some sort of negatively charged ion, that's an acid. All right. Now, technically, I should have written aqueous on all of these, but oftentimes that is not done, and we just assume that it's aqueous. Okay. Aqueous just means that it's in solution, it's in water. We'll talk more about that a little bit later. All right. But a lot of times you'll just see it this way. So once we know it's an acid, then we got to decide, is it a 2-element acid or is it an oxyacid? And the question is, right, does it just have 2 elements or does it have 2 elements and oxygen? So which one is this?
Oxyacid?
Oxyacid, right. So we know we got to go down here to oxyacids. Now, oxyacids themselves, there are 2 different types. There are the ones in which the polyatomic ion ends in 8, or the ones in which the polyatomic ion ends in "ite." Okay? So we look at the polyatomic ion here, it's PO4. What is PO4?
Phosphate?
Phosphate, exactly right. PO4 is phosphate. So we're talking about this branch of the nomenclature flow chart, right? Because it ends in 8. And when it ends in 8, that means that the base name of the oxyanion is used with the ending "ic." And remember, last time I said this really quickly, but you can help you remember this is to say, "ic, I ate an acid," right? So "ic" and "ate" go together. If you see 8, you're going to use the ending "ic," right? So the name of this thing then is the name of the base name of the ion, phosphor with the ending "ic," phosphoric acid. Okay, does that make sense? Okay, let's go to the next one, HCl, ionic molecular acid.
Acid?
Acid. Again, remember, the first thing you got to ask yourself when you name anything is, which one of these 3 things is it, right? What kind of beast is it? Is it an ionic compound, a molecular compound, or is it an acid? This one's an acid. Then you just go back down to the next step. Is it a binary acid or an oxyacid? Binary. Okay, so you just come straight down here. Aha, hydro, base name of the nonmetal plus ic acid. So this is going to be hydro. Base name of the nonmetal is chlor. The ending ic, and acid, hydrochloric acid. Right? Then we have one more to name here, H2SO3. Again, ionic molecular acid.
Acid?
Acid. So we come down here. Binary or oxy?
Oxy?
Oxy. What's the name of the polyatomic ion?
Sulfite?
Sulfite. Very good. It's sulfite. So that means we go down this branch, right? And so now instead of ic, it's going to be us, right? So it's going to be sulfurous acid, right? Does that make sense? Any questions on naming any of these things?
So I have a question. For the acids, it's the hydrogen that's kind of the first, like the fact that it has hydrogen and it's also 2 nonmetals.
Correct. So there'll be now, I mean, there are some things that will be written with hydrogen first that aren't acids. For example, water, right? That's H2O, but they're not very common. Most of the things that have hydrogen in front are going to be acids.
Okay, thanks.
Okay, Asher?
Hey, my question is, if we identify a compound as ionic, how do we know if it can form multiple types of ions?
Yeah, so look back at go watch the lecture from last time again, and you'll see that it's based on the periodic table. So there are certain parts of the periodic table. Most main group elements fall into this category. Most transition elements fall into this category. Okay, but that's how you know. You basically got to know those charts and know where the element falls.
Okay.
Let's see, Emily.
So for the last one that we did, the sulfurous acid, for ones like that, like how would we know that something like that would be sulfurous acid versus sulfous acid? And are we just supposed to know the base name of everything?
Yeah, if you put sulfous acid, that would be fine as well.
Okay.
As long as you know that ending "us," right? Because, but yeah, you look at if you just look at this, it's sulfite. So why isn't it sulfus? Well, it just, there's some little details like that just by convention is the way you do it. So So sulfur becomes sulfurous. Sulfide becomes sulfurous. Sulfate becomes sulfuric. Okay. But you'll have some practice on these in the problem set. And again, if you were to name this sulfus acid, I'd give you full credit.
Okay.
Okay. Good. All right. Thanks. All right. Thanks, everyone. We have to move on here because we still have a lot to cover today. If you have more questions about nomenclature, please stay after class and we can cover those. Okay. All right, let's move on to formula mass and the mole concept for compounds, right? So we already talked about molar mass and the mole concept for elements. Formula mass is the identical thing for compounds, all right? So for a compound, to get its formula mass, you just add up the individual masses of all of the atoms in the formula, right? So for example, if you were to find the formula mass for something like water, let's say, right? H2O, it would just be 2 times the mass of hydrogen, right? Plus 1 times the mass of oxygen, right? And you'd add that together, and that gives you 18.02 atomic mass units for the formula mass of water, right? The formula mass for a compound is equivalent to the atomic mass for an element, right? And in terms of moles, the molar mass of a compound is equal to its formula mass, but it also is equivalent to grams per mole. So for example, for water, its molar mass is 18.02 grams per mole, right? So that works as a conversion factor between grams and moles for water, right? Just like the atomic mass works as a conversion factor between grams and moles for elements, okay? So for example, we can do problems like this. How many molecules are in 50 grams of CO2, right? So we got 50.0 grams of CO2, right? And we want to know, okay, how many molecules, right? So we need the formula mass for CO2. So the formula mass for CO2 is going to be 1 times 12.01 plus 2 times 16.00, right? 12.01 is the carbon, 16.00 is the oxygen, right? And that gives me 44.01 grams per mole, right? So I can use that as a conversion factor between grams and moles, right? So to work out this problem, right, I'm just going to start with 50.0 grams. And then I'm going to use this molar mass, but how am I going to use it? How am I going to write it?
You want grams in the denominator and moles in the numerator.
Exactly right. It's going to be 1 mole over 44.01 grams, and my grams are going to cancel. So now I've converted to moles, but notice the problem is asking me to get all the way to molecules, so I need one more step. What is it going to be?
Avogadro's number.
Yeah, perfect. 6.022 times 10 to the 23. Now I'm going to use it as molecules per mole. Remember, we've been using it as atoms per mole, but Avogadro's number could be Avogadro's number of anything, right? So when you work that all out, you get 6.84 times 10 to the 23 CO2 molecules, right? So the molar mass is a conversion factor between grams and moles. Okay, let's see if you got that. So I'm going to have you try it. Go ahead and try to answer this question. Everybody see the question?
Yes.
Yes, great. Thank you. Okay, 10 more seconds. Okay, so the right answer is D. And majority of you got that, so very good. Basically, you just go 15.0 grams times 1 mole over 18.02 grams. That cancels times 6.022 times 10 to the 23 per mole, right? And you get 5.01 times 10 to the 23 molecules. Okay. Again, most of you got that. Good job. Thank you. Couple of things, right? I really encourage you to learn. You got to do it, right? So if you're not doing these, if you're not answering these polls, you're wasting the opportunity, right? So get involved. Answer the polls best you can. By applying it, that's how you learn it, right? I also want to encourage you, if you don't mind, to turn on your cameras. I see a lot of you do have your cameras on, but a lot of you still have them off, which is fine. You can keep them off if you want, but again, it's better for me and it's probably better for you to remain engaged if you turn them on. And that way I can maybe connect your name and face, even though there's a lot of you, okay? But I can't see you, and I look through, and I am trying to connect names and faces. So if you want to turn your camera on, I would love it if you did that. Okay, very good. Let's go on. The next topic that we want to cover, now that we know formula mass for compounds, is composition of compounds. All right. So, for example, let's say you are a person who has high blood pressure. So, who knows what in our diet contributes to high blood pressure?
Salt.
Salt, right. So, what is salt? Salt is sodium chloride. All right. And it's not the sodium chloride itself that contributes to high blood pressure. It's actually the sodium ion, right? So when you eat a certain amount of salt, not all of that is the sodium ion, right? Only part of it is, only some percentages, right? So composition of compounds is kind of asking, okay, how much of sodium chloride is actually sodium, right? And typically we want to know that information by mass. So if you eat 10 grams of salt, right, how much sodium are you getting, right? Because there's a specific amount of sodium that you should try not to go above, right? And if you want to know that, then you got to know sort of how many grams of sodium you're eating. But if you just track the grams of sodium chloride, that doesn't track the amount of sodium, right? So you need to know something about the composition. So there's something called mass percent composition, which has this formula: mass percent of element X is equal to the mass of element X in 1 mole of the compound divided by the mass of 1 mole of the compound. So for example, for sodium chloride, right, the mass percent of sodium is equal to the amount of sodium in 1 mole of the compound. Well, the atomic mass of sodium is 22.99 grams per mole. So 1 mole of the compound contains 22.99 grams, right? Divided by the mass of 1 mole of the compound, which is just the molar mass of sodium chloride, which is 58.44 grams per mole, right? So 1 mole is going to weigh 58.44 grams. And then we're going to multiply that, right, by 100%. And that's going to give us the percent of sodium, right, in sodium chloride. Yeah? So sodium chloride is 39.34% sodium. So if I eat 10 grams of sodium chloride, right, how much sodium am I getting?
3.9 grams, give or take.
Yeah, exactly right. 3.9 grams. Okay. So does that make sense? The way mass percent works, it tells you how much of each element is in the compound. All right, so let's do another one. Let's determine the mass percent of chlorine in CaCl2. All right, and I'll let you try this one. So go ahead and try figuring that one out on your own. What is the mass percent of chlorine in CaCl2? All right, try to finish up the next 10 seconds or so. Five, four, three, two, one. All right. The right answer was C. And let's see. Ooh, a lot of you missed that one, right? So what's going on? Let's see. If you look at the formula, right? The formula is CaCl2, yeah? So what you have to do is you have to go 2 times the atomic mass of Cl. Why 2? Because the formula has a 2 right here, right? So there's, if you're figuring out the mass of chlorine in 1 mole of CaCl2, you got to multiply it by 2. So 2 times the atomic mass of chlorine divided by the atomic mass, sorry, the molar mass of the compound, right? So that's going to be equal to 2 times 35.45 grams per mole divided by, now that this is the molar mass of the entire compound, right? So you got to do calcium, 40.08, plus 2 times chloride, right? 2 times 35.45, right? And that is all times 100%. Does that make sense? I think maybe some of you forgot to multiply by 2, or maybe you forgot to multiply by 2 down here, right? But when you multiply that out, you're going to get
63.
Yeah, it's for CA instead of CL.
Is this wrong? Let's see, 35.45 times 2.
Yeah, I calculated the same thing. Got 63.88 roughly.
You did. That comes out. So this comes out to be 63.88.
Yeah.
Yes.
Which is none of the above. Ha! Sorry, I must have had a mistake in here.
It's right for CA though.
Oh, I see. I see. That's the CA amount. Yeah, got it. Okay, my bad. Sorry about that, you guys. It should be 63.88%, right? So you can see how your professor can make mistakes as well. I will remember to fix this. Okay, so it should be 63.88 is the right answer. So D is actually the right answer, none of the above. Sorry about that. Any questions on that? Okay, let's move on. Let's learn how to use this percent composition as a conversion factor, right? So here's a question. How many, we saw earlier that for sodium chloride, the mass percent was 39.34% sodium. So what does that mean? 39.34% sodium means, and whenever you see these percentages, it's really helpful to work the problem this way, where you do 39.34 grams of sodium per 100 grams of sodium chloride, right? When you see numbers like this, write them like this, because that's the way you're going to use them in calculations, okay? So, so we say, okay, how many grams of sodium? So you eat 6 grams of salt. You want to know how much sodium did you get? So you write 6.2 grams of NaCl, right? And then use the conversion factor. How am I going to write this conversion factor to get to grams of sodium?
NaCl on the bottom.
Yep, NaCl on the bottom, correct. So I'm going to write 39.34 grams of sodium per 100 grams NaCl, right? And that's going to cancel. And I'm going to get, excuse me, 2.4 grams of sodium, right? So that's how you can use this mass percent to convert from one element to another. Okay, good. All right, so now we can also, turns out we can get conversion factors directly from chemical formulas. So I just showed you how to use mass percent to figure out, okay, how much sodium is in a certain amount of sodium chloride. But it turns out there's actually an easier way to do that. You can get it directly from the chemical formula itself. All right, so the chemical formula tells you relationships not between masses, but between moles. All right, so for example, this chemical formula tells you that there's 2 moles of chlorine for every 1 mole of CCl2F2. And you can use that as a conversion factor between these two things. All right, so for example, we could ask how many moles of hydrogen in 10 moles of water? Well, from the chemical formula here, right, we can write, 2 moles hydrogen is the equivalent of 1 mole of water. In other words, every mole of water has 2 moles of hydrogen. How do I know that? Because there's a 2 here, right? If there was a 3 here, I'd write a 3 here, and so on, right? So if I have 10 moles of water, I'm just picking easy numbers here, 10 moles of water, how many moles of hydrogen do I have? How would I use this conversion factor to figure that out? How would I write the conversion?
Multiply it by 2 moles of hydrogen over 1 mole of H2O.
Exactly right. 2 moles hydrogen, 1 mole H2O, right? And this cancels, right? And I find out, I have 20 moles of hydrogen. Does that make sense? Yeah? Awesome. Okay. So question for you, go ahead and try this. Same idea, different formula. All right, 10 more seconds. All right, the right answer is C, right? So here's the conversion factor that you write, right? 4 moles of carbon and 1 mole of C4H10. And then you start out with the amount of C4H10, 5 moles C4H10. And now how are you going to write the conversion factor to convert to moles of carbon? What goes on top?
4 moles of
4 moles
carbon.
of carbon.
Right. 4 moles of carbon over 1 mole C4H10. That cancels, right? And then you get 20 moles of carbon. All right. And most of you got that, so good job. Okay. Now, that's pretty straightforward, right? Moles to moles. But what if we want to know grams to grams, right? So suppose we want to know how many grams of hydrogen are in 10 grams of water. So I'm going to start setting up these problems like you've learned to set up problems already. You're given, right, 10 grams of water, right? And you're trying to find grams of hydrogen, right? Now, quick question. Can you just say, oh, okay, I know that it's 2 to 1. So can I go 10 grams of hydrogen times 2 grams of hydrogen for every 1 gram of water? Does that work?
No.
No, right? Because that does not work, all right? And that's a very, very common mistake. You can't do that because these are relationships between atoms, right? And the atoms weigh different amounts, right? A hydrogen atom is much lighter than an oxygen atom, right? And that would never make sense anyway, that you have 2 grams of hydrogen for every 1 gram of water. That violates mass conservation, right? So what you got to do is a very common thing that we're going to do over and over this semester, okay? It's a certain pattern, and it's this. It's going to go mass to moles to moles to mass, okay? When you're trying to get from mass to mass, you got to go through moles in order to get from one to the other, right? So you're going to start out with 10, and let's say 10.0 grams of water, right? How do I convert to mass of water? What do you use?
You use the molar mass of water. in one-
Correct. 1 mole over 18.01 grams, right? Now I have, notice I have moles of water. Okay, so I've gone from mass to moles. Now I'm going to go to moles of the other thing, right? The thing I'm trying to find, right? And I'm going to use the conversion factor that I get from the chemical formula itself, all right? So how am I going to write this conversion factor?
2H, 2 hydrogen atoms,
Yep, exactly, over.
1 mole of water.
Correct. Does everyone see that? I'm writing 2 moles of hydrogen over 1 mole of water. Right? Why? Because I'm trying to get from moles of water now to moles of hydrogen, right? Then once I'm at moles of hydrogen, then I can go to grams of hydrogen, right? I can use the molar mass of hydrogen. Now my moles cancel, and now I get my grams of hydrogen, 1.12 grams of hydrogen. Yeah? Does that make sense? All right, let's have you try one. Sorry, no, let's do, yeah, let's have you try one. Go ahead and try this one.
I have a quick question
Yeah.
regarding sig figs on that problem. If you're dealing with 10 grams of H2O, do you only have 2 sig figs in your answer?
Yeah, you know what, that should have been 10.0. So I have 3.
Oh, okay.
It was my mistake, sorry about that. Should have been 10.0 that was given. All right, so try to figure out how many grams of carbon and 5.55 grams of C4H10. Remember, you're going to go from mass to moles to moles to mass, okay? And let me give you, just to save you a little bit of time, the molar mass of C4H10. C4H10 has a molar mass of 58.12 grams per mole. Okay, 10 more seconds. See if you can finish up the next 10 seconds. All right, the right answer is A, 4.59 grams of carbon. See if I got that one right. I think I did. Sorry about that before. So you go from grams to moles. So here's a conversion. You start with 5.55 grams, right? That's what you're given. Yeah. And then you're going to convert that to moles. Grams are going to cancel. Now you got moles of C4H10. Now you got to use the conversion factor that comes from the chemical formula, right? And you're going to convert from moles of C4H10 to moles of carbon. So how should you write it?
4 moles of C over 1 mole of C4H10.
Exactly right. That's going to cancel, right? Now you got moles of carbon. Now you can go to mass of carbon. That's going to cancel. And that's going to give you 4.59 grams of carbon. Does that make sense? So keep this in mind, grams to moles to grams, or mass to moles to mass, right? We're going to be doing that many, many times throughout the semester. Okay, I see a few questions, so let me get to those. Michael.
Yes.
Mike,
Sorry, from before. It's all good.
Okay. Hey, Yoon.
Okay. So I just have a quick question. So I thought for the so once you get to grams of carbon, I thought you're supposed to like multiply like 12.01 times 4 for that one because
No, no, the 4 is coming into play right here. See, you got the 4 to play right here because that's 4 moles of carbon for 1 mole of C4H10, right? So yeah, this conversion factor comes right from the formula.
Mm-hmm.
But now you're at moles of carbon. How much does a mole of carbon weigh? 12.01 grams, right? Not 48 grams.
Oh, okay. So, because I thought you had to like multiply like 4 again because there's like okay, thank you.
No, Delia.
Oh yes. So for the question above, since hydrogen is a diatomic, do we like it would?
Yeah. Good question. You're talking about you're back on this one.
Yeah, it was like the 10 grams of.
Right. So hydrogen is a diatomic. So if you're talking about H2, then yes, it's always multiplied by 2. But what are we talking about here? Is this H2 or is this H1?
Oh, so it's just H1. Okay.
Just H1. So that's why you use 1 gram per mole.
So if it was diatomic, you would multiply the 1 gram.
Correct.
Just making sure. Thank you.
No, good question. Any other questions? Okay, good job. Let's see. I think I'm going to skip this for right now because we're running a little tight on time. All right, so the next thing we want to look at is determining the chemical formula from data, okay? So we already know that we can go from a chemical formula, right, to, for example, mass percent composition, right? We just learned how to do that. The question is, can we go the other way, right? And the answer is yes, we can, all right? So let's just, in other words, we can go from mass data, it could be mass percent composition, or it could be actual masses to get chemical formulas. In fact, this is how people normally figure out a chemical formula of an unknown compound, right? So let's say, right, here we go, we have a sample of a compound. And again, I want to encourage you, a lot of times, you know, people look at a problem and they don't even know where to begin, right? So a good place to begin is always to separate. Okay, what are you given? What is the problem asking you to find? Because that's going to help you to start think through how to solve that problem, right? So in this case, you're given 0.857 grams of hydrogen, and you're given 6.86 grams of oxygen, right? And what are you trying to find? You're trying to find the empirical formula. So let's think about this for a minute. You're given masses of the two elements in the compound, but an empirical formula is a ratio of what? Is it a ratio of masses?
No, ratio of the atoms.
Ratio of atoms, or a ratio of moles of atoms, right? It can be either way. It can be ratio of atoms or ratio of moles of atoms. So what you should do here, right, in these kinds of problems is always first convert to moles, right? So moles of hydrogen, right, are equal to 0.857 grams of hydrogen, right, times 1 mole per 1.01 grams. I'm just going to use the molar mass, and that's going to give me 0.849 moles of hydrogen, right? And then moles of oxygen, I'm going to get the same way, right? 6.86 grams of oxygen times, but now I got to use the molar mass of oxygen, right? 1 mole over 16 grams, yeah? So that's going to cancel, and I'm going to get moles of oxygen, and I end up with 0.429 moles of oxygen. So now I know that when I decompose the compound, I got this number of grams, right? But that corresponds to this number of moles, right? And remember, the chemical formula is a ratio of moles. So I can write a sort of pseudo formula, right? A kind of chemical formula by just writing H 0.849, oxygen 0.429, right? That's kind of a pseudo formula, but we don't like formulas like that because they're not very pretty, right? Even though it is a ratio of moles, I would rather have round numbers. So the way I get round numbers is I just divide by the smallest one, right? And if I do that here, I find that I get H 1.9801, right? And this basically rounds to 2. So really the formula is H2O, right? So notice I went from masses, right, all the way to my chemical formula, okay? And so we're going to be spending, actually, most of the rest of this chapter is about doing this in different variations of that same idea, right? How can I get from mass data like this to chemical formulas, okay? Is this part clear?
What if you had like 1.5 for hydrogen?
If it came out to 1.5 here,
You
then you can
multiply it to
it all by 2, yeah, to get round numbers. Yep.
Okay, as long as it's a round number, that will be the empirical.
You're ultimately
formula.
looking for round numbers, yeah. Diana, did you have a question?
Yeah, we're always going to have to convert it into moles before
Correct.
we do, and then we have to divide it by the sum of both of them.
By the smallest one.
Oh, by the smallest one.
By the
Okay.
smallest one. See how I divided by the smallest number here to get round numbers?
Okay.
So here's the step. Let me give you a step-by-step procedure. A lot of these problems are going to involve using percentages, right? So this is kind of the steps we're going to follow. So let's go ahead and try a problem using these steps, okay? Because a lot of times you're going to be given percentages. It's more common than being given straight grams. If you're given grams, you can skip this first step, all right? Like we just did with H2O. But if you're given percentages, you're going to convert to grams. And then you're going to convert to moles. And then you're going to write this pseudo formula, right? Like we did here. Using the moles as subscripts, right? And then you're going to divide by the smallest number. And then you're going to make it a whole number. All right, so let me I think it's easiest with an example. So I'm going to put this back up in a minute, but let me show you the problem. All right, so, and again, I'm going to set it up. Given. So I'm given 72.4% iron in this compound, right? And I'm also given the atomic mass of iron. All right, and then the rest of it is oxygen. And if it's only these two elements in the compound, what's the percentage of oxygen? What must it be?
28.6.
28.6.
27.6.
27.6. Yeah, sorry.
I think I have a mistake in my notes here. Hang on for a second. Sorry, my bad. Hold on one second. 27.6. Okay. Yeah, so 27.6% oxygen, right? And the molar mass for oxygen is given 16.00 grams per mole. And again, I'm not using the molar mass for O2. Why? Because this is just O, right? There's no 2 there, all right? If we had elemental oxygen, then it would be O2 and we'd use twice that. But this is not elemental oxygen. This is the oxygen in this compound, right? It's not elemental oxygen, all right? So, so there we go. And then we're trying to find the empirical formula. Okay? So now that we have the information, I'm going to go through these steps, all right? So step number 1, convert the percentages to grams, right? So if I have 72.4% iron, right? And I'm going to convert that to grams. Well, I'm just going to, you can assume any amount of the compound, but let's just assume 100 grams to keep it easy, right? So that means I'm going to have 72.4 grams of Fe and 27.6 grams of oxygen in this 100 gram sample, right? Second step is to convert grams to moles, right? So second step, convert grams to moles. Okay, 72.4 grams of iron times, what's my conversion factor? How do I convert from grams of iron to moles of iron?
0.85 grams.
Right here, I'm going to use this, right? And how am I going to write it? What goes on top? Moles or grams? Mole, right? 1 mole over 55.85 grams. That's going to cancel, right? And that's going to give me 1.30 moles of Fe. Are you with me? Okay, I'm going to do the same thing for oxygen. 27.6 grams oxygen times 1 mole over how much?
16.00 grams.
16.00 grams. My grams are going to cancel, and that's going to give me moles of oxygen. I get 1.73 moles of oxygen. All right, so there's my step 2, convert grams to moles. All right, step 3 is I'm going to write a pseudo formula. So what's going to be my pseudo formula? Fe what?
1.3.
Yep, Fe 1.30, oxygen 1.73. But again, I don't like formulas with those kinds of odd numbers, right? I want to make them round numbers. So my next step is going to be to divide through, right, by the smallest. Smallest number is 1.3, right? So I'm going to write Fe 1.30 divided by 1.30, and then oxygen 1.73 divided by 1.30. Does that make sense to everyone? And that's going to give me Fe1, 1.33. Okay, still not round numbers, all right? And then it says multiply all mole ratios by a number to make all whole numbers, to make them all whole numbers. And then you can skip this if they're already whole numbers. But in this case, they're not whole numbers, right? So we got to multiply by some number to make them whole numbers. What are you going to multiply by to make both of these whole numbers?
3.
3, yeah. So just look for the number that you multiply one. It's going to be some integer, right? That's going to make them all into whole numbers. So that's going to be 3, right? So Fe1, 1.33 times 3, right, is going to be equal to Fe3O4, right? Fe3O4, okay? And so that is my empirical formula. Does that make sense?
So anytime you're given a percentage of an element to turn it into grams, you simply take the percentage value and then just change that to gram units?
Yeah, but the reason you're doing that is because you're assuming 100 grams of the compound, right? You could assume 50 grams if you want, and then you'd take, 72.4% of 50, right? But that just makes more math for you, right? So assume a nice round number like 100, and then you just say, okay, in 100 grams, there's 72.4 grams of iron. Does that make sense? Daniel. Daniel Bollinger, you have a question?
Yeah.
Can't hear you.
Oh, yeah, sorry.
Oh,
How did you know?
Sorry, Danielle. I was calling you the wrong name. Danielle, go ahead.
Are you able to hear me?
I can hear you, yeah.
Okay. How were you able to or how did you know to multiply it by 3?
Because I know that I'm trying to make this. So for example, let's say one of these fractions is 1.5. What would you multiply by to make that a whole number?
2.
2, right? What if it was 1.25? What would you multiply by? 4, right? So you just look and you say, okay, what can I multiply this by? Because one of them is going to be 1, and the other one, if it's some fraction, you figure out what do you multiply that fraction by to get it to be a whole number.
Okay, thank you.
Yeah, good question.
I have a question.
Yeah.
So is it possible for you to skip step number 4 if you just see like what the mole ratio is? Like when you divide, like if you do 1.3 moles of the Fe over 1.73 moles of the oxygen, you get a 75 ratio.
Yeah, you can, but it doesn't always work.
Oh, okay.
Sometimes it's hard, because sometimes it's really hard to see it. In this case, you're right. You could see that, but in other cases, it's not going to be quite so obvious. So this procedure will always work is the nice thing, no matter what the ratios are. Okay, I'm going to have you try one. I'm going to put it up here, and I'm going to have you go ahead and write that down, and then I'm going to put the procedure back up. So I'm going to give you about 20 seconds to write this down, write down these, and then I'm going to put the procedure back up so you have that procedure, and I want you to go ahead and try it. Okay, and here's a periodic table so you can get all the different molar masses. So I want you to try this problem. All right, does anybody need more time to copy it? Okay, finish copying it. Everyone got a copy? Anybody else need more time? Okay, awesome. So I'm going to put the procedure back up so you can see it, and go ahead and try to work this problem. Get the empirical formula.
Professor Chow,
Yeah.
would you mind showing the answer or the options?
Yes.
Thank you.
Professor, can you put up the questionnaire thing? Not that one. The like the A, B, C, D, E thing.
It is up. The question?
Yeah. No, the boxes that we select.
The poll is up.
Hey, okay.
It's probably hidden behind your screen or something.
Yeah.
Like move the Zoom window.
Yeah.
Okay, we're running out of time, so I'm gonna go ahead and let you keep working on this, but I'm gonna also show you what the answer is. The correct answer is B, and the way you get that is you take each of the grams, you convert to moles, right? So you convert carbon to moles of carbon, grams of hydrogen to moles of hydrogen, grams of oxygen to moles of oxygen, grams of nitrogen to moles of nitrogen, right? Once you get those moles, you write the pseudo formula, right, with all of those numbers. Then you divide by the smallest one. The smallest one in this case is 0.07243. Sorry, 0.7243. So you divide all of those by that number, right? Right, and then if you do that, right, you'll get C7H8O2N1, right? So that's your empirical formula. Okay? Does that make sense to everyone? I know we're kind of a little rushed there at the end. Let me just say one more thing, take one more second just to show you one other thing, and then we'll be done. The empirical formula is not the same as the molecular formula, okay? The empirical formula is, remember, the molecular formula is some multiple of the empirical formula. So if you have an empirical formula, right, times some integer n is going to give you the molecular formula, right? So for example, hydrogen peroxide, its empirical formula is OH. You multiply it by 2, sorry, its empirical formula is HO. You multiply it by 2, right, and you get H2O2, its molecular formula, all right? So in order to go from the empirical formula to the molecular formula, you need some more information, right? And usually the other information is the molar mass of the compound, right? So the molar mass of the compound is going to tell you, if you have the molar mass of the compound and you have the empirical formula, you can figure out what this N is, and then you can use that N to get from the empirical formula to the molecular formula, all right? So that's what we'll pick up next time, because we're out of time right now, but I'll show you how to get the molecular formula from the empirical formula if you have the molar mass of the compound, all right? You might be able to figure it out just from what we just did, but that's what we'll start next time, okay? All right, I'm going to go ahead and formally end class there, and I'm going to stop the recording. You're welcome to hang around, and I'll answer questions and whatever else you want to do. So I'm going to stop the recording, and class is officially over. Thank you for coming. Those of you that want to hang around, I'll see you in a bit.